If there's one thing we know about life, then it should be that little remains the same, often changing. And if we go back and look at our inductor circuit a little more closely, we discover some interesting effects when things change. Inductors. It turns out that if we use a switch to connect a coil to the voltage source and are quick enough to take a close look at the flow of juice, it's possible to see that the inductor tries to resist change. With the resistor, juice flows instantly, but with the inductor it took time for the current to build up, and the greater the inductance, the longer it took. It's as if the inductor is resisting change as the magnetic field builds up. Let's now modify our circuit. If we connect two voltage sources and connect a variable resistor across the two, and tap into the middle here, then as we move the wiper we can raise to a positive voltage and down to a negative voltage. This can push and pull juice around the circuit. Connect it to a coil. If we slowly move the wiper, the voltage rises and falls and the current follows dutifully. The speed we change the wiper can be measured in the number of times a second we perform a complete cycle. Once a second, 1 cycle. Twice a second, 2 cycles. Cycles per second are given in Hertz, after the German inventor Heinrich Hertz, who discovered radio waves. Let's tidy things up and use this new symbol for this signal source. And now increase the frequency. Look, as the frequency increases, so does the lag between the voltage and the current. That's the effect of inductance. Swap the inductor for a capacitor. We know what a capacitor does. It does not allow juice to flow. So, as we slowly raise and lower the voltage on the plates goes up and down too. As it does this, when it is positive, a positive charge appears on the top plate and a negative one here on the lower plate. Half a cycle later, everything is swapped around, with the lower plate being positive and the upper plate being negative. The larger the capacitor, the greater the charge it stores, but importantly, nothing flows across the capacitor. In here is an air gap or an insulator that prevents it. Let's increase the frequency of our signal. As we do, we notice that the time taken to move the charge between the plates becomes more and more significant. Juice rushes back and forth around the circuit as the frequency increases, and it almost looks as if it is crossing the gap in the capacitor. But notice, the current leads the voltage. This leads to the aide-memoire CIVIL, civil, where we note that with a capacitor, C, current, I, leads voltage, whereas with an inductor, L, voltage leads current. Thus we can gain a greater feel of our three components. The resistor is fairly passive, just passing current as ohm tells it to. The inductor treasures its magnetic field, looking like a short circuit at low frequency and DC, and heavily resisting change at high frequencies, so it looks like an open circuit. The capacitor treasures its store of charge, and a good capacitor will hold its voltage forever, which can make it dangerous if it's just sitting there waiting to discharge through you. At low frequency, it looks like an open circuit, but as the frequency rises, more current appears to flow, so at high frequency, it appears to be a short circuit. These are our three perfect components, and how they work and appear to change based on the signal frequency.